Hello, everybody. Thank you very much. First of all, the slides for my talk are available online at this address, people@igalia.com/Morandeira/2022 I put it already also in the chat of the conference, just in case anybody wants to follow along or have a look at the links and so on. Today, I am going to be talking about the work that we have been doing on ad filtering and declarative net request over the past months. In this talk, I'm going to describe a specific problem that came up in the transition to the declarative net request API. Then I will describe the API that we are, see that? Sorry. Sorry. Yeah, so basically I'm going to be talking about this problem that came up in the transition to declarative net request, the API that we are proposing, the different approaches that we follow for the implementation, and finally some initial benchmarks of this kind of show that we are in the right approach. This is still all a work in progress. I think we will be getting more concrete results, I hope, in the next few weeks and months. But this is still, as I said, work in progress. And then finally, I have some conclusions about the general experience of contributing to the Web Extensions API. So we start with the status as it was until very recently. As you know, in the previous version of the extensions platform, you can use the Web Request API. And the model for this API is that the extension is able to intercept network requests directly. And this gave extensions a lot of flexibility, also in terms of how and when the different filter lists could be updated. On the other hand, web request does have some drawbacks, particularly because the extension needs access to a lot of personal information from the user. And also there are some concerns, some aspects of the performance that could be improved. The interesting feature for us here is that with web request, it was possible for the extensions to fix a problem that happens when a rule is found to be harmful, found to be misbehaving after it has been distributed to users. This is something that happens from time to time. This is a good example. It happens to Google Docs. There was an error in EasyList that broke Google Docs last year. And within 24 hours, the extension developers, the blocker developers, or blocking developers, were able to be notified of the problem, identify the cause, fix it in upstream, and then provide solutions for the users, because either the users could wait for the filter list to be updated automatically, or they can also even trigger a manual update. And so it happened very quickly. It was a pretty visible problem, and there are some headlines like, blockers are causing issues, disable your blocker, etc., because of course it directly impacts the way a lot of people work nowadays. I brought that up a couple of tweets just to show also the difference in time. There's a few hours between both of them, between the developers identifying the issue and working on it, and then being able to provide a solution for the users. So this quick turnaround, this ability to respond to one of these problems fast is very important to maintain. The problem that we find in Manifest v3 and the move to declarative net request is that in declarative net request, the extension does not intercept directly the network requests. Rather, it provides a list of rules to the browser, and then it's up to the browser to evaluate and modify the network requests on behalf of the extension. There are most of the rules belong to the static rule sets that are bundled with the extension, and there's a certain number of additional dynamic rules that can be added and removed one by one. This is just in case you are not familiar with the details of the API, but basically the update enable rule sets is the method that you use to enable and disable some of these filter lists, rule sets that have been bundled with the extension. And it is also possible to update, to enable and disable individual rules dynamically. Although in this case, there's a limit to how many dynamic rules you can have that is much lower than the number of static rules that you can include with the extension. And the specific issue that we are working on is that fixing problems in these static lists will become harder than it used to be with declarative net request. Because there are some workarounds, but they all have some drawbacks. Because these static filter lists can only be updated when the whole extension is updated. If there is a problem in a filter list, your choices are basically to either disable the whole list or wait for the extension to be updated, which can take some time. No? And it is possible to try to fix a misbehaving rule, static rule, by adding a dynamic one, but this can also cause some side effects, and we can look into that in more detail. So the tricky part of adding a new rule dynamically is that both the old broken rule and the new rule will be active at the same time. So usually a rule is broken when it blocks too much, and then the inverse of that rule will have the opposite problem and allow too much. These are some examples, real examples of rules that eventually made it into easy list and then were quickly fixed, quickly removed because they were problematic. So this first one is a typo. This word media was intended as a comment, but it actually was entered in the list as a rule that blocks everything that has media in its URL, which means that it breaks the internet, basically. But on the other hand, if you want to undo a problem like this, if you want to undo a rule like this, you have to add the opposite. Add a rule that allows everything that has media on its internet, which means it could be allowing things that shouldn't be allowed. The second one was a rule that was intended to be a rule. It's not a typo, and it actually worked well at disabling, at blocking some content that should be blocked, content that has the add CSS path in its URL. The problem is that it also blocked some legitimate content that should not be blocked. And again, we have if you want to fix this with a dynamic rule, then you have the same issue of allowing things that were before being correctly blocked. And the third rule is interesting because it blocks content from a particular domain. But if you look into that domain, it turns out to be a CDN content delivery network that hosts loads of things from loads of different people. So we cannot know ahead of time if something that is hosted there will be desirable, will be harmful, should be blocked, should be not blocked. So again, if we have a rule that blocks everything, then the inverse would allow everything, and that's also not something that we necessarily want. Usually, the real fix, the fix that is done in the upstream list is to remove the broken rule and maybe introduce a new one, introduce a fixed one, maybe a more specific one that does exactly what we want. And from our point of view, to fix this kind of problems, it would be much easier to be able to simply disable problematic static rules one by one. So basically, our proposal is to provide a way for extensions to disable individual static rules in declarative net request. And this would allow developers to react quickly to rules that have undesirable behavior without losing functionality or risking unwanted side effects, and also without significantly affecting performance or security. So when it comes to designing the API and the implementation, we need to take into account the rate at which we expect that ad blockers will want to disable static rules. So how many rules would this affect? And could this be maybe misused? Could it be abused somehow? We have to look at this. So on the one hand, we have the use case that I just talked about, where this functionality will be used for situations that are similar to the issue with Google Docs that I explained earlier, where there's a rule or a few rules that need to be disabled because they are found to be harmful. But on the other hand, thinking about realistic use of this functionality, we have to ask, what is the maximum plausible, reasonable, likely rate at which ad blockers might want to use this functionality? And from our point of view, our starting point is that ad blockers might try to match the rate at which rules are disabled in the upstream version of the filter lists. So if you are including EasyList in your extension, we expect that you would be disabling rules there more or less at the rate at which they are disabled in the upstream EasyList, which in that particular case means roughly removing a few hundred rules per week. So this is a very, very rough estimation, but basically we, for a typical collection of filter lists, we estimate that about 1,000, maybe 2,000 rules can be removed every couple of weeks. So this is not to say that this is how people would use this functionality, but it's just to say that this is something that our implementation in our API, in our performance, should contemplate. That we should take care that this use case is correctly served. So after several iterations and experiments, this is our current API proposal. First, we propose a method, update static rules, that is able to disable and enable individual rules within one static rule set. Changes to the rules take effect immediately, or if the rule set was disabled, then the next time that the rule set is enabled, those rules will not be enabled with the rest of the rule set. These changes are persistent until the extension as a whole is updated, which is also when the static rule sets will be updated as well. Basically, our goal with this API is to prevent a rule from accidentally becoming enabled when it shouldn't be. And finally, because in declarative net request, there is a global count, a global maximum number of static rules that can be active at the same time, a disabled rule should not count towards this global maximum. This is the ideal definition of the method, which is also mentioned in the more detailed API proposal document. This is the second method that we are proposing, which is simply a method called getDisabledRules that returns the list of rules that are disabled within a particular rule set. Basically, so the developer can have a view of what is the current state of the extension. So talking about the implementation of this API, in Chrome, the implementation of declarative net request does a number of steps. First, it parses the JSON lists of rules that have been provided by the extension. It indexes these rules and then stores them in the disk in a format that is called flat buffer. And the flat buffer format stores the rules along with an index. So indexing the rules in this way provides for efficient matching when we are checking if a particular request matches any of the rules, and also allows data to be loaded from disk to memory very efficiently. The main drawback of the flat buffer format in general, or in this case, is that the process of turning a JSON list of rules into an index flat buffer file takes quite a bit of time. And most of the time, also, updating a flat buffer file is not possible without recreating it, recompiling it completely. It is possible to update small fields that have a fixed size, for example, but not to add and remove entries. And besides, there is some interesting value if we are able to keep the compiled filter lists from changing. For example, if the compiled rule sets are predictable, then maybe we can check if they have been modified. We can check if they match the expected value. The extension can provide a checksum, et cetera, et cetera. So basically, taking all of this into account, we have tried different approaches to the implementation. The first one was a very simple one, which is that when you disable rules, we recompile the flat buffer, but removing those that have been disabled, which worked well at runtime, but was actually very inefficient way of enabling and disabling rules. Another one that we tried is to add, as I mentioned, a flag to the flat buffer file, so we can indicate if a particular rule is disabled or not. And this worked, but it's actually quite complex to implement and to maintain, and also might not be usable by other browsers, which have their own way of implementing declarative net request. Finally, this is our current approach to the implementation. First of all, we keep the compiled flag buffer files immutable without changes. And we store the list of disabled rules for each rule set separately from the compiled file. Right now in our implementation, we are storing the disabled rules in a small JSON file for each rule set. But we are still talking about this with the Chrome team, and we might change that and store the list of disabled rules in the general preferences of the browser. When a rule set is loaded, we also load the list of disabled rules for that set. And then the matching algorithm, the one that checks every incoming network request to see if it matches any active rule, holds both the list of rules and the list of which ones among them are disabled. And it checks the active rules, and if a match is found, then the algorithm will check if the matching rule has been disabled before it returns a result. And this actually has pretty decent performance. We have been doing some initial benchmarks, looking in particular at 3 areas: at the performance of disabling rules, of loading rule sets that are partially disabled, and of running the matching algorithm for a given request. I want to stress that these are preliminary benchmarks for our current implementation. Is basically a way to see that this approach is feasible. This is a good idea. But as I said, the implementation details will still probably change. In these benchmarks, I have been using only one rule set with 20,000 rules. In each case, I am disabling up to 2,000 rules, like that's 10% of the rule set. And the measurements were taken in my development machine, so things should look for the trend more than the specific number. So the first benchmark is for the time that it takes to disable static rules. In this first case, we are disabling the rules in bulk. We are disabling a bunch of rules all in one go. First 100, then 200, then 300. And the time that it takes to complete this operation grows slowly with the number of disabled rules. But in a realistic scenario, we would not be disabling rules in these huge chunks. We will be probably disabling them incrementally as they become problematic or as they are removed from upstream. So in this other benchmark, I am disabling the rules 100 at a time. And you can see that the rate at which the performance becomes a little bit slower is it's much more gentle. The increase in time when you are updating the rules incrementally actually means a pretty small difference in terms of time, which is, as I mentioned, the more realistic scenario. The next benchmark, sorry, is the time that it takes to load a rule set that is partially disabled, that has some disabled rules. As we can see in the graph, while there is an increase in time as more and more rules are disabled, the value in absolute terms remains small, the increase in the actual time that it takes to complete the operation. In this case, there's a difference of about 4 milliseconds between no disabled rules and 10% of the rules are disabled. which is not a huge increase. And finally, we have several benchmarks for the time that it takes to find a matching rule for a given network request. And interestingly, it turns out that the main factor influencing this metric is whether the request is matched by a rule or not, and in the case where it's matched, whether that rule is located at the beginning of the filter list of the rule set or towards the end. And the reason is that these are all factors that determine the amount of work that the matching algorithm will have to do. They will determine the number of rules that will need to be tested. So this is the baseline performance when the matching rule is the very first one to be checked. And as you can see, this metric is not really affected by the number of disabled rules. The trend remains flat. Whereas this is the metric when the matching rule is the very last one in the list, the very last one to be checked. And first, you see, obviously, that it's significantly slower than when the match is at the beginning of the set, but also that there's actually, as you disable more and more rules, a trend downwards, because the matching algorithm has to do less work, because there are fewer rules that need to be checked. This is pretty much the same result that we get when a network request is not matched by any rule in the set. This means that all of the rules have been evaluated and none of them has been found to match this request. And again, the values are pretty similar to the ones in the previous case, and we also see this gentle slope downward as you disable more rules and you have less work for the matching algorithm to do. So we can put the last three graphs together and highlight trends. And here what we can see is that as the number of disabled rules increases, the performance of the fastest scenario remains roughly the same, and the performance of the slowest scenario is in a slow trend downwards. So the conclusion is that disabling more rules does not harm performance. As conclusion of these benchmarks, it seems that our implementation adds a small performance penalty for disabling large amount of rules and for loading a partially disabled set, but this is not a big penalty by any means. And it does not seem that disabling rules has a significant impact in the performance of the matching algorithm. So as I said, this is still an initial approach, but it looks like we are on the right path. The details of the implementation might still change because we are still working with the Chrome team to refine it and to get it ready for inclusion. At the moment, all of this is still at the proposal stage. We are talking with the engineers of the Chrome team about our API proposal and implementation. We are also updating the web extension working group so we can gather feedback from other browsers and extension developers. And if you want to participate in this work, the issue listed there at the web extensions working group is probably the best place to get a broad view of the current state of this proposal and the best place to gather feedback from all sorts of different people in the community. Finally, I wanted to have some conclusions about the general experience doing this work. First, from my point of view, Manifest v3 does introduce some interesting innovations, and there is room to adapt it to new contexts and new use cases. But at the same time, it is true that the process for specifying web extension APIs is not as well developed as is the case with more mature web standards. Nevertheless, I think people in the summit and people in the community should be aware that there are forums where they can contribute in the open to the evolution of this platform. In this case, probably the best place to start is the Web Extensions Working Group, where people from different web browsers and from extension makers get together to discuss additions and changes to the extensions platform, because it is a good place to discuss possible new functionality and to also check how it would interact with the needs and the implementation details of the different browsers and the use cases of other extensions. Finally, because I think I am a bit over time, I just wanted to thank a few people. First, I wanted to thank eyeo for organizing this summit, for sponsoring this work, and for helping us in getting a good understanding of this very challenging field. Thanks as well to the Web Extensions Working Group, which has been a great place to gather feedback and evolve this proposal. Thanks also to the Chrome team who have been reviewing our work, specs, and code. Thank you to my colleague Byung-Woo, who has been doing a lot of work on the implementation and helping me evolve and mature all these ideas. And finally, thank you to all of you for attending. Thank you very much.